So let's look at another problem. This is a homework problem that I assigned. So it's a quiz I've used in other classes as well. So what we have is Big Papi at home plate. He's going to try to hit a home run over the green monster, which is this big wall you see in the background. And as you see, there's a yellow line coming across this wall, and as long as you hit that line or go above, you get a home run. And it turns out that line is 37 feet above the bottom of the field here. So we've got a 37-foot wall, and the distances from home plate to the walls in the background are shown by this map. And Big Papi's headed right for this point here, which is at 379 feet. So the question is, given his hitting information, can he make it over this wall? And so we have some handout that you have, and he starts by hitting the ball 4 feet above the plate. And I'm going to rough out a little diagram here, and we'll clean it up on the next page, but just to get some of the ideas down here. So we've got a ball somewhat above the ground here. All right, now he hits the ball 30-degree angle, 120 miles per hour. All right, so there's our 4-foot ball. So here's we're going to go 30-degree angle, 120 miles per hour. Now, 120 miles per hour, not good units to use. We're going to convert to feet per second. So we know 60 miles per hour is 88 feet per second, so 120 is double that. So we have 176 feet per second as our initial velocity. Okay, now we still have an issue because we know this velocity is in 2 dimensions and we need to break it down to x and y. We'll do that on the next page. Let's just set up some basic information here first. Here's the big monster, big green wall, and they gave us some information about that. At the point he's aiming towards, it's 379 feet away. That's an x position, and its height is 37 feet. This picture is not drawn to scale. I've got 4 feet over here and 37 feet over here, but it's sort of hard to draw this one to scale given this is 379 feet in this direction. Okay, so let's set this up a little bit more formally here. And our question is, when Big Papi hits the ball given those conditions, does it make it over the wall or not? And he only has to hit at 37 feet to get the home run. So it has to be 37 feet or above when it reaches the wall at 379 feet. So we already have our initial point here with our velocity vector. Draw our xy axes in as first step. We're drawing our diagram. I'm just going to throw a wall down here so we can visualize a wall. And here's, roughly speaking, a path that we would draw. Sorry, a little bit lumpy here. But hopefully he's going to make it over the wall. We don't know this. It could be low, it could be high, who knows. And there's the position we're interested in identifying. And right off the bat, because we picked up our y-axis right through the ball where it starts, we have our initial position is 0 in the x direction. And of course, we knew that it was 4 feet high when it starts, so it's 4 feet above the ground. Now, we've got to decompose this vector. Now, as I mentioned before, a lot of times it's easier if I have some nice open space up here just to move this vector up and decompose it up here to keep the clutter on our diagram minimal. So I'm going to do that. So here's our vector, here's our 30-degree angle. I'm going to draw some horizontal lines and some vertical lines to box that in. And I can take any of these sides to get my upward and rightward components. So I could go up and to the right, or I could go to the right and up. And so I'm going to go to the right and up. Alright, and you notice I have a 90-degree angle here. X and Y axes are at 90-degree angles, so that means I have a 30, 60, 90 triangle. And on a 30, 60, 90 triangle, the short side, which is right here, is always 1/2 of the longest side. And so this 176 divided by 2 is 88 feet per second. So upward we have positive 88 feet per second. So there's our Vy naught. Our Vx naught on a 30, 60, 90, well, this medium-sized side is square root of 3 times longer than this side. So I can take this side to be 88 square roots of 3. And if you work that out, don't put radicals, please, in physics work. Crank it out of your calculator. 3 significant digits is 152 feet per second, positive. So we're moving positive to the right and positive up. Now, we need our initial conditions. Our initial conditions are based on assumptions that we make. And what assumptions do we typically make for a ball flying through the air? Well, typically we assume that it is free fall. The only force acting is gravity, and gravity acts downward, causing our negative 9.8 meters per second squared. Forces cause acceleration. So we're going to get a negative 9.8 meters per second squared, but we don't want meters per second squared here. We want US units, so we're going to use feet per second squared. It's negative 32, so please keep that in mind, that we need US units when appropriate here. So we're going downward at negative 32. Now our acceleration of the x we're assuming is 0 if our air resistance is negligible. Of course, the question is this really a good assumption? We've got a ball traveling at 120 miles per hour. Put your hand out the window of your car at 120 miles per hour. Of course, you'll never do that because you'll never drive that fast. But your hand would have experienced a huge amount of force acting on it, as this ball will do. So sure, this is not a great assumption here, but at least it'll give us a starting point to figure out a path, and then we could maybe fine-tune it later with some more physics to figure out how air resistance does act on it. Now our point of interest over here, what do we know about it? Well, we know exactly how high this wall is and how far away it is. It's 37 feet high and it's 379 feet away, and we need to find the actual time, position, and velocity of the ball as it gets over here. So step 4, let's use our initial conditions and set up our equations. I'll just flip through these real quick. There's our equation, plug in our numbers, and there's our simplified equation. Here's the position versus time, and velocity. Here's plug them in, and as we see, as usual, under a free fall situation, which technically this is not, we know that, but we're going to assume it is, the ball moves constantly at 152 feet per second in the x direction. It doesn't change if we assume there's no forces other than gravity acting downward. In the y direction, gravity is acting on this, and so our y simplifies to this equation, and our velocity is affected by gravity as well, and we have this equation. How do we solve the problem? Well, we know, we're going to use the numbers we know. We know that the y value is 37 feet at the particular point we're looking at, and we also know that the x is 379 feet. So we could actually use either one of these pieces of information to plug it into either the y equation or over here into the x equation. Take your pick. I'm going to use the x. Alright, so I'm going to plug in 379 feet into my x equation, which I did right here. Solve for t, really easy solution for t. We get 2.49 seconds for it to move 379 feet to the right. So we're at the green monster. Question is, now that we're at the green monster after 2.49 seconds, how high are we? Well, we can plug it in. We can plug into 5 to figure out the height of the ball. That'll tell us if we have the home run. We can plug it into 6 to get the velocity of the ball. So let's plug into 5 first, and we find out that we're actually 124 feet above the ground. Now remember, the green monster is only 37 feet. So this is 4 times taller than the green monster. Now I've been to Fenway Park many times and I've seen a lot of home runs hit. I've never seen one go 124 feet above the ground at the green monster. And the problem with our little scenario here is we're not taking into account free fall is not true here. It's actually air resistance involved. So what we can do to show you the difference, we'll simulate it on the FET Canon simulation and see what happens. We'll do that in class. Alright, let's just take a look at the velocity, and the velocity turns out to be 8.32 feet per second. The ball is still moving upwards, you'll see, and that gives us a little clue here. The ball is still moving upwards, so we haven't quite reached the apogee yet. So not only is this a towering home run, it hasn't even reached its highest point yet. This thing's going forever. I'm not sure this might land in the river, in the Charles. And so that's our solution. So our conclusions are, yeah, he makes his home run by a long shot. And this is major, but we know our assumptions for air resistance are not good, and so what we'd have to do is try to figure out another way to include air resistance. But for starter purposes, this is a good little calculation to do to give us an idea of what it could do if we pumped all the air out of Boston and let him hit a home run. But later on, we'll run a simulation just to see what this really does.